This is ST300 week 9. Welcome back, everyone. And in today's lecture, we're looking at classification models. After the 2 hard weeks of looking at the theory, I'm sure now you'll be glad that we're finally looking at some applications. And the good news is that since we've covered the theory, you see now the application sides will be we'll go through cover the material fairly quickly because the discussion is much easier than the theory. A recap from last time. Well, we finished off the MLE by introducing the iterative weighted least squares algorithm. And then we covered hypothesis testing. That was the world and the likelihood ratio. We're looking at 2 types of models here, the binary response models and the multinomial logistic regression. Okay, so the motivation is, let's the response variable, the y variable, be binary, so taking values 0 to 1, and some examples are default on loan payments, so classify as 1 if there is a default, 0 if not, detection of insurance fraud, and lots more other things. So it has wide applications. And this kind of data is widely seen, and so definitely we need some kind of a model for it. Example here, default on credit card payment. So what we have, let's look at the left panel, is that we have the balance to pay off on the horizontal, and on the vertical we have probability or default. Well, observations we see for each person is either 0 if no default and 1 otherwise. So this is highlighted by these yellow dots. Okay, so you can see like for lower balance, probability people are not defaulting, but when you reach more higher balance, there's now defaults, and there is some region where there's overlap in these balances, where some people around like 1,500 don't default and some default. And then as your balance increases, then the no defaults, they kind of start to fade out, and people start to default. Well, that starts to kind of increase, as you can see by the intensity of the dots. So if we think back to part 1 of the course, we could treat the balance as the covariate, and then the y variable 0 and 1 as the response, even though it's not normally distributed. And if we were to fit by OLS a simple linear regression, we would get this blue line. And for various reasons, there is disadvantages of using this approach. And then we'll argue that on the right panel, this is the logistic regression. Some of you heard of, probably one of the most famous of all the GLM models. And we'll be looking at that shortly. So let's focus to the linear probability model, because that's like an obvious place to start to develop a better methods for modeling binary data. Okay, so what is the linear probability model? Well, I said it kind of informally, but let's just state what that is. So we're modeling the mean here. It depends on some function of the covariates. And so y is Bernoulli, so 1 or 0s. You know the mean for a Bernoulli is the probability. And notice the yi here, and the probability I is not just a fixed pi. It can vary over observations. Because remember, for the GLM, all we need to do is assume independence, but we don't have to assume they're identically distributed. So this gives us the linear probability model if we just regress the y on the x or x's. All right, so disadvantages of doing this one. Well, the probabilities, you can see, you can lie outside the permitted regions of 0 to 1. Also, what this does is it assumes some linear relationship, and that's not necessarily reasonable. You can see in the logistic in this model that you can have this non-linear relationship. There's inherent heteroscedasticity. That's not really an issue. I know you can deal with that using some robust errors or something like that, so that's not too crucial. Error term is not normally distributed, so the MLE is not the same as OLS here, so OLS is not the most efficient here. So an alternative to the linear probability model, we can use a model that has the binomial error structure. Okay, so now we've shown in theory, on the theory side of GLM, that a Bernoulli Bernoulli distribution belongs to, is a member of the one parameter exponential family. And what we know is that the dispersion parameter phi is 1. And for this reason, you'll see that when you run the GLM, you'll see that in the output, it says the dispersion parameter binomial is 1. Okay, that is the phi. Now, the bit highlighted in blue here, this is the theta. And so that's, you know, then that is the natural link. That's the canonical parameter. That's going to be the natural link. So the binomial GLM that uses the this canonical link, which is called a logit link, now that is called a logistic regression. It's also known as like the binary or binomial logistic regression to distinguish it from some other types of logistic regression. So you can see here that it is function of the probabilities, and it's equal to the linear predictor. Okay, if we rearrange that equation for the probability, that gives us the so-called logistic function. So here we've got the probability now as the output, and the input we've got the covariates. And the logistic function is an example of a sigmoid function. So sigmoid function is a function with of this characteristic S-shaped or sigmoid curve. So here you've got the eta here. So the eta will be scalar, and then you've got probability. Okay, so that is this graph here is of this. It doesn't actually have to look in typical plots. When people are telling you about the sigmoid logistic function, they plot it like low on the left-hand side, increasing probabilities as you increase right. But you can have it the mirror image, so you can have like this shape as well. Interpreting the parameters, so exponentiating the equation, that logistic function there, and let's drop the I subscript for clarity. Okay, so we have this expression. Now the point is like when we interpret the coefficients, what we're arguing on this slide is that we don't interpret the coefficients directly. We don't just interpret each beta. It's a more common sense thing to do something else, which we'll talk about now. So the left-hand side of this expression, that is called the odds. Odds by definition is like probability of success here divided by probability of failure. So if the odds is equal to 1, it means there's equal chance of success and failure. Odds greater than 1 indicates higher chance of success, and less than 1, lower chance of success. Important to note here that there's not a one-to-one relationship between probability and odds, right? So if odds goes up by 10%, it doesn't mean the probability goes up by 10%. So when we're dealing with logistic regression, it makes it more natural to interpret things as odds just because of this functional form. You can still talk about what happens, like if you have a covariate and you talk about unit increase in the covariate, what's the associated increase in probability, but there's a bit more work to do there. From the output, it's more direct to interpret it as odds. So unlike linear regression, now we can interpret not just the beta for each individual beta. So this is just a particular beta for one of the covariates. We exponentiate it. So exponentiate the beta, and that will give us the odds ratio, which is this guy here. Oh, how many? Yeah, the odds ratio. So this is the odds, and 1 unit increase in X is going to increase the odds by a factor of this guy here. Okay, do I need to write something here? Maybe I should write something here. So this guy here, let's call this the original odds. Oops. And then if we increase, okay, let's just write something. Let's just do it for a simple example. Okay, so let's say we've got one covariate and it's continuous like this. Okay, so how about if X goes up by 1 unit? Then the new odds, let's call it subscript n for new, is going to be equal to, okay, X goes up by 1 unit. So write that, which is, can you see it is going to be that. Okay, therefore, this is called odds ratio. So if we look at this line, so 1 unit increase in X is associated with a factor change of the odds by e to the b, this guy here, isn't it? So it's more because it's multiplicative. So the new odds is going to be changed by whatever this is. So if it's bigger than 1, then your new odds is bigger than the original odds by, it's going to increase the original odds. Whereas if it's less, if this factor is less than 1, obviously now your odds is shrinking. So that's how you'd interpret if you have covariate, so the covariate is continuous, and if your covariate here, if your predictor, your X variable is a factor, then you can interpret like we did in part 1 of the course, then it is a change in odds compared to the reference group. Making predictions, so once we've fitted the model, we can just use, we can obtain predictions via, via the logistic function. So we just plug in certain, we've got the betas hats here now, plug in for certain values of X, which are in our date sample, and within our sample range, and then compute the probabilities. So you can follow this, for example, this. Okay, now there is a latent variable formulation. Latent just means unobserved, and formulation of the logistic regression. And let's present it. So let's say y star here is the unobserved variable. And then let's suppose, okay, so this first row, that's like a usual multiple linear regression. But remember, the yi star is unseen. But it's connected to what we do see, and what we do observe is 1 or 0s, right? So this is why we do observe 1 or 0. So if we say that y is 1, it's like it's triggered to be 1 if this y star, which is continuous, is exceeds this threshold 0. Okay, and the error term has a certain CDF, which is to be specified, and specifying the CDF of this in certain ways gives rise to slightly different models, which we'll come on to shortly. Now, the interpretation, so why do this? Well, the interpretation of the y star and the y depends on the context. So for instance, an economist may view y as a binary choice, such as purchasing or renting a home, whereas the y star represents the utilities of purchasing and renting. So if we again drop the subscript, then the probability at y is 1 is the same as saying that this continuous variable y star is bigger than 0, the threshold 0. But what is y star is equal from the previous slide. You can see that the y star is this bit here. So substitute that over here into the second line and rearrange. And the idea is we want to kind of express this in terms of the CDF of the error. And so that's what we have. Okay, so going up here, just view this. Probability at y is 1 is the same as 1 minus the CDF of here. And the CDF here is some function of beta. And it's got your covariates in there. If the distribution of this error term is symmetric about 0, then obviously this holds, that you guys obviously see that. And depending on the choice of f, we have certain kinds of models. So two popular choices of the CDF are, so if we choose it to be the standard logistic distribution, this gives rise to logistic regression. Okay, so basically it's like an alternative derivation of logistic regression, this latent variable approach. If we define it, the CDF, as the CDF of a standard normal, this gives rise to the so-called Probit model. Okay, both these, you can see, imagine guys, both these are kind of sigmoid functions, right? The S-shaped curves, as I show you on this slide. So you can see here that the red is Probit and the green one is the Logistic function. So both symmetrical around 0 here. The difference is really in the tail ends. Now, some courses might make more of an emphasis about, oh, which tail is bigger, but all intents and purposes, for us, that difference, it's not important. Now, how do we fit the GLM in R? Well, we use this Glm function. And I've highlighted here in this box, this is the key difference from the Lm function. We have to say the family. So this is like the family, which distribution does y belong to? And we have these choices. You can see in the left column. And in the right column, it gives you the default link function. So this is the G function. So for the binomial, this is used, it has the default function, the logic function. In other words, by default, it's going to fit the logistic regression. Now you can change these, so this will have some other options, but here we need to look up the documentation. Notice it also has the Gaussian family, which is basically just the same as the Glm function. All right, so to look at some output, some kind of example of something that you might see, let's continue with this default data. So default is coded 1 and zeros. And we just set family equals binomial, and we're leaving on the default link function. So that was going to give it the logit function. In other words, we have logistic regression. Right, so what we have is we've got, just like the Glm function, we've got some statistics on the estimates. Something to point out here is, can you see that instead of having a t value, we have a z value? Because everything here, the inferences here now is done by, is large samples. And recall that this is estimated by IWLS algorithm. Dispersion parameter already noted that the binomial family is 1. Okay, then we've got the null deviance and residual deviance. And since phi is equal to 1, you know that residual deviance is also equal to the scaled deviance. And the scaled deviance follows some chi-square distributions under certain assumptions for individual GLMs, which we'll turn attention to that later. Okay, so Fisher scoring iterations, well, it says Fisher scoring, but it's doing it by IWLS, but basically IWLS is implementation of Fisher scoring. So it's conversion 8 iterations. So here is an example of how you might interpret in this case, we've got one single covariate to the balance. How you might interpret when you have a $1 unit increase. So 1 unit increase, $1 increase in the balance. And this maths I actually did earlier in the slides. All right, so it's done the calculations here for you. So odds ratio exceeds 1. So here it corresponds to about 0.6% factor increase in odds. I highlight in yellow just to emphasize, I can't emphasize enough to you guys that when you're interpreting by default, you know, these are not cause and effect interpretations. It's not saying if we increase $1, that will lead to, it will cause this new odds to increase by, the odds to increase by a factor of about 0.6%. Though we've run the logistic regression with y being binary, 1 and zeros, we can actually run it in terms of looking at viewing each yi as from a binomial distribution and by grouping the data. So here we distinguish between grouped and ungrouped. They lead to equivalent MLE estimates. So it's best to show you example here what it looks like. So suppose I have the data here. This is ungrouped because the y's are binary, 1s and 0s. I'm going to take the same data and group it. So what I see here, suppose x is 3, covariate 3, we've got y and x, you see x is single covariate, x is 3. Okay, so we've got 2 x's there and there. So in that group, m is 2, right? Using this notation, it's m is 2. Why? Well, what's the number of successes in 2 trials? Well, there's only 1 of them, so that's 1. Likewise, when x is equal to 9, okay, there's only 1 of them, so let's just take x is 11. 11, there are 3 of them, right? So m is 3, and out of the 3, how many are 1s? 1, 2, so there's 2. So this here, in this case, look, your y's is now binomial, where m is bigger than 1, well, bigger, doesn't have to be 1. So now there are, so these are binomial, and we can still use logistic regression. In fact, it's actually for hypothesis testing, it's better if you can, it's better to run it as grouped if you can. So why is that? Because if we want to do inferencing involving deviance or Pearson statistics, now here's the condition: we need to use grouped data with a reasonable number of observations in each group. And here is a rule of thumb. And so why do we need to do that? It's because, as I said, in theory, to kind of remind you, is that the usual likelihood ratio asymptotics doesn't hold, right? Because n is increasing, but your degree of freedom on this chi-square is n minus p, so that's also increasing. Although in ungrouped data, you can't use this deviance statistic, you can still use the Wald test, i.e. this guy here. That's called a Wald. All right, so an example here, guys, is for grouped data. So what we see here is we have a table has 16 cells for success and failure. Okay, in other words, this is 8, that is 8, so that's 16 cells. That why I denote the number of workers who develop the disease after X number of years of exposure. Yeah, so I realized I didn't kind of explain the background, but I suppose you can just read that. And if we run it, now we have, I've highlighted here the null deviance and the formula for that, and the residual deviance and the formula for that as well. And since this is group data and phi is 1, this guy here we know follows. And do we have enough observations in each cell? Well, you've got a 0 right there. And a rule of thumb is requires about 80% of expected frequencies in both success and failure groups to be greater than 5. Okay, well, that's not greater than 5. That's not greater than 5. That's not greater than 5. Okay, so, but you get the idea that it is a rule of thumb. So it would be better if it was like that. Now, supposing it was like that, then we can interpret interpret the residual deviance. Okay, and do a hypothesis test. So that would be testing the current model fits well versus the current model is not fitting well. And yeah, we can just compare to, we could compute this p-value, for instance, here. So it's bigger than 0.1, so we do not reject. Okay, but that's only, remember, that's supposing that we have this condition is met, and if we look at the table, there's about 19% of the cells that have less than 5 observations. Okay, but that's something to bear in mind when you're doing this test. Certainly you can't do it when the Y is ungrouped. This here is to show you the difference between a saturated and null model. This probably would have been better last week, I would have thought, but I wanted, it fits more in this week's lecture because this example is for binary data. So I've got these dots here, 1s and 0s, and this is the X covariate. So the green line here, that is like the probability is just constant. It does not depend on the value of the covariate. Well, that's not a surprise because this null model here just assumes no covariates. It's just a single parameter. So that would just be the sample mean, in other words, sample proportion of the Y. The saturated model assumes each observation is the parameter, so you can see that's why it goes for it's a perfect fit, okay? Because it's useless as to generalize for the data. And the red here is our fitted model. Maybe one thing to add to this is earlier I did kind of say straight line relationships here, but not modeling probability is not so suitable. And we can see from here is, for instance, like over here in this range of X, there are no ones. So then this must be close. Okay, whatever the probability must be close to 0. Whereas when we start to have overlaps here, you've got to, it depends on the concentration of the dots in zeros and ones. So it can't be really linear. So it's kind of, that's why you get this curve. It's more kind of that's intuitive way of seeing it anyway. Why you can't really, a straight line isn't really suitable. Okay, now logistic regression, it makes the assumption, as you will have seen in the homework, that the probability that you're trying to model cannot contain the endpoints. So it's like it falls in an open interval. And so if you get a case where that the pi is 1 or is 0, logistic regression will fail. Here is an example. So X and predicted probability, here's your observation. So here you've got for low values of X, okay, zeros. Where you've got high values of X, ones, but there's no overlap. So it's quite clear. We can see that pick any threshold here between like around here to over here, can put a straight line down there and say anything to the left must be 0 probability, anything to the right, must be 1 probability of 1. And when I say left, I mean like if I pick this 50, for example, I say anything lower than 50, and this will be the eta. This axis is eta, so anything to the left of when eta is less than 50, well, we'll classify y as 0. And if it's eta is greater than 50, we'll classify y as 1. And we don't have to say that's what happens when eta is 50. There's no 50s here. And although prediction, you probably have to go with one or the other, but yeah, but that's not the not the lesson here. The lesson is like if you have this separation called complete separation, that means that the logistic regression will fail. And let's illustrate that with a simulation. So I've created 10 observations for y of 1s and 0s, right? So the first 5 observations, I'm using the rep function here for the saying repeat the value 1 5 times, repeat the value 0 5 times. So it's going to give me a 10 by 1 one-dimensional array of 5 1s followed by 5 zeros. And then I'm just going to have x as a sequence from 1 to 10, and then I'm going to plot it, and that's what you can see on this panel here. So notice right at the start when I said the sigmoid function doesn't necessarily sweep from low to high in this shape. It can sweep from, this time we will expect something like that, right? If logistic works. But we're going to find logistic doesn't work. You can see here by construction, I've simulated it so that there is a separation here between the 1s and 0s, right? I can draw a line, for example, right down here and say anything to the left of this x is 1, classify y as 1, otherwise classify as 0. And if we run this, so GLM, y and x, family binomial, then I've highlighted in yellow, what happens is you get error warning messages. So algorithm did not converge, okay? And it's in telling you, you've got fitted probabilities here, which is actually 0s or 1s. Right here, so it does not fall into the open interval. Okay, so it's failed. All right, good. So let's take a short break, and when we come back, we'll look at some a real life example of how you can apply this logistic regression. Okay, so let's look at the study here. It was reported that death rates were seen to be highest for among Black and Asian ethnic groups. It's coming to COVID-19. And so why is this exactly? I mean, is it to do with ethnicity? Or is it some other reason that people in these groups have a higher risk for some other reason? Maybe there's some disadvantage, maybe some kind of social or something like that. And the conclusion here is ONS saying is that Office of National Statistics in the UK says that the greater risk in England and Wales is largely due to life circumstances. Okay, so let's look at the study here, a bit more details. Okay, so here is a paper, predictors of outcomes of those hospitalized patients with COVID-19. So what this paper does is it describes characteristics and outcomes for people hospitalized for COVID-19 in a number of hospitals in London. What statistical method did they use to study the data? They used Logistic Regression model. Now, where did they get this data from? It's a retrospective cohort study of all patients. Okay, so it's looking back, and this is the data of that period. And so what they did, they used logistic regression as well as some other methods performed to evaluate what factors or predictors associated with COVID-19 hospital mortality. And the way they're using the factors here is another word for predictors. It's not like our use of the word factors in R. Okay, some descriptive statistics. So we can see like of these, among these ethnic groups, and there's just a bin for every other group, other people that don't fall into these 1, 2, 3 groups, and there's also a missing group, right? So we see that distribution of ages. I'm looking at Asian, Black, and White here, more or less the same, right? Oh, big, large overlaps in the boxes. Okay, and just to show you the results here from the study, from the fitting a logistic regression. And they fit this logistic regression for age and these other 2 differences, these of the ethnic groups. And what we were interested in is looking at the odds ratios. So logistic regression, so as we said, natural interpretation of these coefficients to get hold of these odds ratios. So the ethnicity here is a factor, white being the intercept, would seem to be here the reference group. Okay, now the point estimates of these guys is reporting, forget the word adjusted for now, let's look at the word, it's adjusted, is the odds ratio. Okay, so for these groups it's bigger than 1, bigger than 1. They're all bigger than 1, right? So that means compared to the white group, there are high odds. But those are based on point estimates. That's not taking account of uncertainty. And recall, guys, in the first part of course, I said when you kind of report estimates, it's also a good idea to report confidence intervals or some kind of interval that represents the uncertainty of your estimates. So if you're Bayesian, that would be a confidence credible interval. But here we're looking at confidence interval, and in the parentheses, and I'm just highlighting the one in blue because you can see that one in blue does not contain the value. Now don't think about 0 here. it doesn't contain the value 1, right? It doesn't contain the value 1. These guys do contain the value 1. So it points to this group here having evidence that the odds for this group is greater than for the reference group, which is this group here. So I'll highlight in yellow here. So after counting for controlling for certain things, you can see the people in this black ethnic group do appear to have increased odds, right? Highlighted in blue. And then, I mean, but do you stop there? No, because then you say further research is needed to investigate whether such an association, notice the word association, didn't say using because it's understands that what you're finding here is not a cause and effect, right? So you have to be very careful about that. It's not necessarily cause and effect. This is not under this data, maybe not under experimental conditions where you can actually isolate the thing that you're looking effects that you're looking for. So it's an association here that you found. Okay, yeah, that's pretty much it. Okay, finally, let's look at an extension to the logistic regression, to the case where the y variable now is just some kind of a nominal variable and multi-class. So multi-class nominal variable. And this here we're looking at the multinomial logistic regression. An instance is, for example, we have an observation. In this case, it's a dog, right? And then we want to classify it. Is it one of these three things? So it's not binary now, because in this case, I got three things. So y, the observation has to be classified as this, this, or that. In case dog, cat, rabbit. All right, we just need to know a slight. So we need an extension for the binomial, and that is a multinomial distribution. So let's say y has j number of categories. Probability of observation being category, taking the j value in category j is, okay, pi subscript j. So assume that the response probabilities are mutually exclusive and exhaustive, meaning that if you sum up all these probabilities, it comes to 1. I don't have to remind you guys, each probability can't be negative. Right, if there are n independent observations of y, okay, okay, you guys, it doesn't help that this doesn't help me that I'm reading this. You can read it yourselves. That the multinomial distribution is, okay, is this guy here. If you set j, capital J is 2, you get the binomial distribution, right? So this bit here will be your n choose. Okay, well, easy to say. This will be your combinatorial bit. You know what I mean? N choose R used to say, n choose X in your when you looked at the binomial distribution. In the multinomial logistic regression setup, we have to pick one of the categories, one of the J things, as the baseline or reference category. So without loss of generality, let's pick the first one. Then the logits for the other categories as modeled as. So we have J, capital J number of our categories. And what we're going to create is 2 to J. So capital J minus 1 number of equations. And the equations are given by the logit ones. So remember that, in other words, this guy here, highlighted in yellow because that is the guy that you are using, the first category you're using as the baseline group. So you're comparing the probabilities of each group to the baseline. You can express this guy in terms of probabilities. Let's just rearrange the thing, and you get this simple rearrangement. Now, if you sum this probability across the J's from 2 to capital J, and you know that all the probabilities add up to 1, which we said from the previous slide, then you get that the first probability for the first being in the first category is this expression. And if you substitute this back into 5, now we've got an expression for the other probabilities from 2 to j. So in other words, line 6 and 7 give you an expression of the probabilities in terms of the parameters. Okay, I think this slide is actually easy to read without me having to say anything anyway. And maybe if I was talking, that actually confuses things. But anyway, it's easy to follow, I think. Yeah, so 6 and 7 can be written more compactly, so now from all categories here, like this, but with the proviso that you've got the eta 1 is set to 0. You have to do that to recover equation 6. Okay, so you can't forget to say that. And this equation that I highlighted in red is called Softmax function, or the standard Softmax function. And like if you're doing machine learning, you'll come across this function, I'm sure. And the Softmax function is a generalization of the logistic function, but it's for multiple dimensions. Oh, okay, spelling error there. Multiple dimensions. And so here is one way about how we can use a Softmax function is that you might have this actually from some kind of, say, a neural net. It outputs some numbers here for these categories like J1, 2, 3, 4, 5. But these numbers here is like, how do you interpret them? You know, how do you interpret these numbers? We've got 5.1 here. Does it mean it's like almost 5 times more likely to be in this category than this category? Whatever you're observing, say, so what we can do if we pass these numbers through the Softmax function, it outputs probabilities, and these are easy. Well, we know how to interpret probabilities. Okay, so for this example, just to note, it was in this category that you would have 1, 2, 3, 4, 5. Yeah, 5 categories. This is multinomial with that many number of categories. Okay, so quick summary. No need to be quick, I guess, because this lecture hasn't been that long. So logistic regression is one of the most commonly used, if not most common, of all the GLMs. Okay, and we've focused on interpreting the parameters here for logistic. And remember, we said that we interpret, it's a natural interpretation in terms of odds ratios here. And then finally, we looked at the multinomial logistic regression, which extends the logistic regression. That's the case where the response is nominal. There are other fancy logistic regressions that we don't cover in the course. For one, there is the ordinal logistic regression. That's the case where the y variables, they can be ordered. But yeah, we've covered the stuff that we needed to do. And in week 9 class, there is a practical I'll leave to you with the logistic regression, and we will go over exercise 8. Okay, we'll go through exercise 8. That's the plan. All right, guys, so thanks for watching as usual, and I'll see you in class.